The Big Bang created the universe 13.8 billion years ago. That's what they teach you. The universe began then. Time began then. Before that, there was nothing. But here's what will shatter everything you think you know. The Big Bang wasn't the beginning. It couldn't have been. And when you understand why, the universe becomes infinitely stranger than you ever imagined. Sit down. Get comfortable. Because we're about to dismantle one of the most fundamental things you believe about reality. Here's the story everyone knows. 13.8 billion years ago, the entire universe was compressed into an infinitely small, infinitely dense point, a singularity. Then suddenly it exploded. The Big Bang, space expanded, matter formed, stars ignited, galaxies emerged. Eventually, billions of years later, here we are. That's the creation story of modern science. The universe had a beginning. Before the Big Bang, there was nothing. No space, no time, no matter, no energy, nothing. And then, bang, everything. This story is taught in every textbook. It's in every documentary. Neil deGrasse Tyson talks about it. Stephen Hawking wrote about it. It's accepted scientific consensus. And it's wrong. Or at least it's incomplete in such a fundamental way that calling it the beginning is misleading. Richard Feynman understood this. He was always careful about what he claimed to know versus what he was speculating about. And when it came to the Big Bang, he'd tell you, we know the universe was once very hot and very dense. We know it's been expanding and cooling for 13.8 billion years, but we don't know if that was the beginning. We can't know, not with current physics, because the moment you try to talk about the beginning, you run into a wall, a fundamental limit to what physics can tell you. Let me show you why. First, let's be clear about what we do know, because we know a lot. The Big Bang theory isn't wrong. It's just incomplete. We know that galaxies are moving away from us, all of them, in every direction. The farther away they are, the faster they're moving. This was discovered by Edwin Hubble in 1929. If galaxies are moving apart now, that means they were closer together in the past. Run the clock backward far enough and everything was in the same place. The universe was smaller, denser, hotter. We can calculate how long ago this was, about 13.8 billion years. That's not a guess, that's a measurement. We can see the leftover radiation from when the universe was young and hot. We call it the cosmic microwave background. It's everywhere, a faint glow of microwaves filling space, the echo of the Big Bang. We can study this radiation. We can measure its temperature, its variations, its polarization. And from those measurements, we can reconstruct what the early universe was like. 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, it was too hot. Matter existed as a plasma, a soup of electrons and nuclei, too energetic to combine into atoms. Before that, even hotter, even denser. We can trace it back to fractions of a second after the Big Bang. We understand nuclear physics well enough to predict what happened when the universe was 1 second old. Protons and neutrons forming, eventually combining into the first atomic nuclei, hydrogen, helium, trace amounts of lithium. We can test these predictions. We can measure the abundance of elements in the universe, and it matches perfectly. The Big Bang theory predicts the exact ratios of hydrogen to helium to lithium that we observe. So the theory works spectacularly well. It explains the expansion. It explains the microwave background. It explains the element abundances. It's been tested thousands of ways and passed every test. But here's the problem. The further back you go, the hotter and denser the universe gets. Keep going back, and you hit a point where our physics breaks down. We call it the Planck epoch, about 1043 seconds after the Big Bang. Before that, we don't know. We can't know, not with current physics. Let's talk about why physics breaks down at the Planck epoch. Physics is built on two great theories: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes particles and forces at the smallest scales. These theories are fantastically successful. General relativity explains black holes, gravitational waves, the orbits of planets, the expansion of the universe. Quantum mechanics explains atoms, chemistry, semiconductors, lasers, all of modern technology. But they're incompatible. They give different contradictory answers when you try to apply both of them to the same situation. Usually that's not a problem. Gravity is important for planets and stars, big things. Quantum mechanics is important for atoms and particles, small things. You rarely need both at once, but in the very early universe, you need both. The entire universe was smaller than an atom. It was quantum-sized, but it also contained all the mass and energy that would become galaxies and stars, enough to create huge gravitational effects. You need quantum gravity, a theory that unifies quantum mechanics and general relativity, and we don't have one. Not a complete one, not one that's been tested. String theory is one attempt. Loop quantum gravity is another. There are others, but none of them are proven. None of them make testable predictions that we've been able to confirm. So when you ask, what happened at the very beginning at time zero? You're asking a question that requires quantum gravity to answer, and we don't have that answer. We can't even be sure the question makes sense. What does time zero mean if time itself is a quantum phenomenon that emerges from something deeper? This is what Feynman would emphasize. He'd say, I can tell you what happened 1 second after the Big Bang. I can even tell you what probably happened 10 seconds after the Big Bang. But the very beginning, the Planck epoch, I don't know, nobody knows. We're speculating. Let's talk about singularities, because this is where the beginning idea really falls apart. In general relativity, if you run the expansion of the universe backward in time, you eventually reach a point where all the matter and energy in the universe is compressed into zero volume, infinite density, a singularity. This is what the math of general relativity predicts. And people took this to mean that the universe literally began as a singularity, an infinitely dense point. But here's the thing about infinities in physics. They usually mean you're doing something wrong. They're a sign that your theory has broken down, that you're pushing it beyond its domain of validity. When you calculate the self-energy of an electron in early quantum electrodynamics, you get infinity. That doesn't mean electrons have infinite energy. It means your calculation is wrong. You need a better theory. Feynman and others developed that better theory, renormalized quantum electrodynamics, and the infinities went away. Same thing here. When general relativity gives you a singularity, it's not telling you there really was a point of infinite density. It's telling you that general relativity is breaking down. You need quantum gravity. And quantum gravity will probably tell you something different. Maybe space and time themselves are quantized. Maybe you can't compress things below the Planck length, about 1035 meters. Maybe the universe wasn't infinitely dense. Maybe it was just very, very dense but finite. Or maybe time doesn't extend infinitely into the past. Maybe time itself has a structure that prevents you from going back to before the Big Bang. Or maybe, and this is where it gets wild, maybe the Big Bang wasn't the beginning at all. Maybe the universe existed before in some other form, and the Big Bang was a transition, not a creation event. So let's talk about what might have come before, because there are several possibilities and they're all mind-bending. Possibility 1, the universe is cyclic. Maybe the Big Bang wasn't the first one. Maybe the universe expands, eventually stops, collapses back in a big crunch, and then bounces into a new Big Bang, over and over, eternally. We used to think this was impossible. We thought the universe would expand forever, because there's not enough matter to pull it back together. But then we discovered dark energy, a mysterious force causing the expansion to accelerate. That complicates things. Maybe cycles are possible after all, just not in the way we originally thought. Possibility 2, the universe emerged from a quantum fluctuation. In quantum mechanics, particles can pop into existence from nothing. Virtual particles. They borrow energy from the vacuum, exist briefly, and then annihilate. This happens all the time at tiny scales. What if the entire universe is a quantum fluctuation? What if it popped into existence from nothing, borrowing energy from the quantum vacuum? This sounds crazy, but the total energy of the universe might actually be zero. Positive energy from matter and radiation, negative energy from gravity. If they exactly cancel, then the universe has zero total energy. And quantum mechanics allows zero energy fluctuations. Possibility 3, The universe is eternal with no beginning. Maybe time extends infinitely into the past. Maybe there never was a beginning. The Big Bang was an event in the history of the universe, but not the first event. This creates philosophical problems. Infinite past, infinite regress, but logically, it's possible. And some theories, like eternal inflation, suggest this might be the case. Possibility 4, time itself began at the Big Bang. This is Stephen Hawking's idea. Maybe asking what came before the Big Bang is like asking what's north of the North Pole. It's a meaningless question. Time began with the Big Bang. There is no before, but even this doesn't really answer the question. Why did time begin? Why this particular universe? Why these laws of physics? Here's something that bothers a lot of physicists. The universe seems extraordinarily fine-tuned for life to exist. If the strength of gravity were slightly different, stars wouldn't form. If the electromagnetic force were slightly stronger, atoms wouldn't bond into molecules. If the expansion rate were slightly faster, galaxies wouldn't form. If it were slightly slower, the universe would have collapsed immediately after the Big Bang. There are dozens of these parameters, and they all have to be just right for a universe like ours to exist. Change any one of them by even a tiny amount, and you get a universe that's either empty or so chaotic that nothing interesting can happen. Why? Why are the constants of nature tuned so precisely? One answer: the multiverse. Maybe there are countless universes, each with different laws of physics, different constants. Most of them are sterile, boring, dead, but a few, by pure chance, have the right parameters for complexity to emerge. We exist in one of those because we couldn't exist in the others. This is called the anthropic principle. We're not in a special universe. We're just in one of the universes where observers can exist to ask the question. But this feels unsatisfying. It doesn't explain why there's a multiverse. It just pushes the mystery back a level. Another answer: maybe the constants aren't arbitrary. Maybe there's a deeper theory, a theory of everything, that explains why the constants have the values they do. Maybe they're the only values that make mathematical sense, and we just haven't discovered the underlying logic yet. Feynman would have hated both of these answers. He didn't like anthropic reasoning. It felt like giving up on finding a real explanation. But he also knew that sometimes the universe doesn't give you the answers you want. Sometimes you hit a wall and you just have to admit, we don't know yet. Let me tell you about inflation, because this is one of the most important ideas in modern cosmology, and it changes what the Big Bang means. In the 1980s, physicists realized that the standard Big Bang model had problems, several problems. Why is the universe so uniform? The cosmic microwave background has almost exactly the same temperature in every direction. But regions on opposite sides of the sky were never in contact with each other in the early universe. They couldn't have exchanged heat. So why are they the same temperature? Why is the universe so flat? Space could be curved, like the surface of a sphere or a saddle. But measurements show it's almost perfectly flat, like a sheet of paper. Why? Why don't we see magnetic monopoles? Grand unified theories predict these exotic particles should have been created in vast quantities in the early universe. But we've never found one. Inflation solves all of these problems. The idea is simple but radical. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. It doubled in size every 1037 seconds. In a tiny fraction of a second, it grew from subatomic size to larger than a galaxy. This expansion smoothed out any irregularities. It stretched the universe so much that any curvature became undetectable. It diluted exotic particles like monopoles to undetectable levels. And here's the key point. Inflation happened before the hot Big Bang that we usually talk about. The Big Bang, as we think of it, is really the end of inflation. It's when inflation stopped and all that energy dumped into creating matter and radiation, heating the universe to incredible temperatures. So what we call the Big Bang isn't the beginning. It's what happened after inflation ended. And inflation itself, we don't know what started it. We don't know what stopped it. We have models, but they're speculative. Some versions of inflation are eternal. In eternal inflation, most of the universe is always inflating. It never stops. But quantum fluctuations occasionally create pockets where inflation ends, and those pockets become universes like ours. In this picture, our Big Bang was just one pocket among countless others. There's a vast, eternally inflating multiverse, constantly spawning new universes. This is speculative. We have evidence for inflation. It explains too much to be coincidence. But eternal inflation, the multiverse, we can't test that, not with current technology. Here's a fundamental issue that doesn't get talked about enough. We can't observe the Big Bang directly. We can only see the aftermath. The cosmic microwave background formed 380,000 years after the Big Bang. That's the oldest light we can detect. Before that, the universe was opaque. Photons couldn't travel freely. They were constantly scattering off electrons. So the first 380,000 years, we can't see it directly. We can only infer what happened based on theoretical models and indirect evidence. And the first few seconds, the first tiny fractions of a second, we're relying entirely on physics that we've tested in particle accelerators, extrapolated to energies and densities far beyond anything we can create in a lab. We're confident about the physics up to a point, but the Planck epoch, pure speculation. We don't have the physics. We don't have the observations. We're guessing. Feynman would be the first to admit this. He'd say, here's what we know with confidence. Here's what we're pretty sure about. Here's where we're speculating wildly. And the very beginning, that's in the speculating wildly category. This doesn't mean the Big Bang theory is wrong. It means we need to be humble about what we claim to know. The universe was once hot and dense, and it's been expanding for 13.8 billion years. That's established. But was it the beginning? We don't know. If you asked Richard Feynman, what happened at the beginning of the universe? Here's what he'd probably tell you. I don't know. Nobody knows. We have theories. We have speculation. But we don't have a tested, confirmed theory of quantum gravity, so we can't say for sure what happened at the Planck epoch. We know the universe was hot and dense 13.8 billion years ago. We know it's been expanding and cooling. We know about the cosmic microwave background, about nucleosynthesis, about structure formation. We have a good theory for all of that. But the very beginning, the moment of creation, we're guessing. And you should be suspicious of anyone who tells you they know for certain what happened at time zero. Maybe the Big Bang was the beginning. Maybe time itself started then. Maybe it doesn't make sense to ask what came before because there was no before. Or maybe the universe existed in some other form before the Big Bang. Maybe it was contracting and bounced. Maybe it tunneled from another universe. Maybe it's part of an eternal multiverse. We don't know. And that's okay. That's where we are. That's the edge of our knowledge. What we should do is admit what we don't know. Keep working on better theories and test them when we can. But we shouldn't pretend we understand things we don't understand. That's bad science. And then he'd probably add, but here's what's amazing. We can understand 13.8 billion years of cosmic history. We can trace it from a hot, dense state to galaxies and stars and planets and life. That's incredible. That's worth celebrating. The fact that we don't know everything doesn't diminish what we do know. So if the Big Bang wasn't the beginning, what's the real mystery? The mystery is, why is there something rather than nothing? Even if the universe is eternal, even if there's a multiverse, even if quantum fluctuations created everything from nothing, you still have to ask, why do the laws of physics exist? Why does quantum mechanics work the way it does? Why is there a quantum vacuum that can fluctuate? You can push the explanation back. You can say the universe came from a quantum fluctuation, but then you have to ask, why does quantum mechanics exist? You can say it came from a deeper theory, but why does that theory exist? At some point you hit bedrock. At some point there's just, this is how reality is, and we don't know why. Maybe there's an answer. Maybe there's a theory of everything that explains why the laws of physics are what they are, why the constants have the values they do, why reality is structured this way. Or maybe there isn't. Maybe at the deepest level, things just are. And that's the end of the explanation. This is where physics meets philosophy. And Feynman would tell you, I'm a physicist. I can tell you how the universe works. I can't tell you why there's a universe at all. That question might not have an answer, or it might have an answer we can't comprehend, or it might be the wrong question entirely. But we can still ask it. We can still wonder. We can still push at the boundaries of knowledge and see how far we can go. So let's come back to the beginning, or rather the beginning. The Big Bang wasn't the beginning, not necessarily. It was an event 13.8 billion years ago when the universe was extremely hot and dense and began expanding. What happened before that? We don't know. Maybe nothing. Maybe time itself began then. Or maybe the universe existed in another form. Maybe it was contracting. Maybe it tunneled from somewhere else. Maybe it's part of an eternal cycle. We don't know, and that's the honest answer. The story you were taught, that the universe began 13.8 billion years ago, is a simplification. It's useful for communication, but it's not the whole truth. The whole truth is messier. The whole truth is, we know a lot about the universe's history, but the very beginning is still a mystery. We're working on it. We have ideas, but we don't have answers. Not yet. And Richard Feynman would want you to know that. Not because he wanted to spread doubt or confusion, but because he believed in honesty, in admitting what you don't know, in being clear about where knowledge ends and speculation begins. The universe is 13.8 billion years old, measured from the Big Bang. But was the Big Bang the beginning? That's an open question. One of the biggest questions in all of science. And someday, maybe we'll answer it. Maybe we'll develop quantum gravity. Maybe we'll find evidence of what came before. Maybe we'll discover we're part of a multiverse. Or maybe we'll find that the question itself doesn't make sense, that time and space and causation all emerge together, and asking what came before is like asking what's north of the North Pole. Either way, the search for answers continues. The edge of knowledge keeps expanding, and that's what makes science beautiful. Not certainty, not having all the answers, but the process of asking questions, testing ideas, admitting when you're wrong, and pushing deeper into the unknown. That's what Feynman understood. That's what he practiced. And that's what he'd want you to understand about the Big Bang. It's not the beginning. It's just as far back as we can see right now. And what lies beyond? That's the next frontier.